Hi, I'm Dietmar. I work for Arm. Some of you guys might know me. Our group, Power Management, Performance Management, we have done a lot of work on the mobile area for Android in the recent years. There were a lot of talks already about ES, CAS-aware scheduling. This one is different here. This is about Arm64 servers. But since server and mobile devices are using the same kind of Linux kernel, we're talking here about the same kind of scheduler strategy or topology, and this is the multi-cluster shed domain. Because the architecture of the Arm64 servers look a little bit different than the more hierarchical structure of x86 or AMD devices, we want to put some thoughts into if both like the ARM flat topology or the hierarchical topology of those other architectures actually can work together without configuring the scheduler differently. So most of the Arm64 servers today, they have 64 to 128 CPUs in a single multi-cluster shed domain, and that's the problem because, or it could be a potential problem because
do they actually share cache? All of them.
They share what we call the distributed cache on the mesh network, and we don't have anything other which is like a smaller structure in terms of classification. So we have no other chance to map.
And is this a uniform mesh, or is there some shape to be found inside of it?
This is what this talk is about, but probably not.
Visible. No, but I mean, if it's there, you might as well expose it, right?
Yeah, but if I mean, the question is how to use it, right? Like in this setup we have in the scheduler, and we all know from the mobile sector and also from the servers. So this is what the talk is about. But we also had, like in early days, we had some really bad outliers, for instance, in terms of topology of the scheduler. Ampere Ultra, Ampere 1, you have like up to, on the one, you have up to 192 CPUs. And when those first test results came out based on those machines, we were asking, how does your scheduler topology look like? And people are just saying, okay, we have only one package level, 192 CPUs. So there was not there was not a lot of scheduling going on at this moment. Select idle sibling or run queue task, fair run queue tasks where you could only choose the CPU the schedule was running on, or the press CPU the task was running on before. So not really a lot of scheduling in the wake-up path. And then we have on the third point to describe something we also deploy right now on the Ultra, Ampere Ultra, Ampere 1, or Ultra Max also. There are 3 machines. They have clustering on this Snoop control unit. So when you have the device interface of the cross point, you have the CPUs and or the request nodes. And in these request nodes, you can have 2 CPUs on the Ultra, for instance, or 8 CPUs on the Ampere 1. And they claim that this is like a cluster. But since they didn't have like a last level cache on the MC level, there was a cluster level, but in wakeup, we never go into select idle sibling because of that. So the 2 levels of cluster in MC actually didn't really make the difference unless you consider only load balance, but this was a minor effect. So what we saw in the code is that they essentially said we have to promote the cluster level onto MC to essentially have wake-up scheduling on those machines. And there was a big fight recently about getting config shed cluster in default, the configuration of the kernel. And people have seen like performance benchmark difference on those machines, but probably not all of them were aware what the actual issue was. Luckily, this is like a neo-worse v1, so we should not deal with this like in recent versions or later versions. The question is also number 4, like this sysutil-based mechanism to figure out how many CPUs we scan in the MC domain to find an idle one. We ask ourselves the question, is there an optimal ratio between MC size and the number of CPUs of a machine? Because if you only have one MC domain, it's a one-to-one correspondence. And if your MC domain only has two CPUs, like on the Ultra, 85% of the capacity, and then you switch off in terms of utilization, it doesn't really align. But it's still working, obviously, right? You don't get a mistake. You might lose a couple of percentage in performance, throughput or latency. And number 5 is more important also for us, like sub-NUMA control on x86 or the CCX stuff on AMD. I mean, you guys are always like nicely aligned when you deploy those things in terms of hierarchy. You have like 20%, 40% of all the CPUs in one MC, and then you have the next level, which we don't have. And again, this could have implications on wake up and load balance as well. And we have cache-aware scheduling as a fair extension. I mean, if you only have one MC domain, you can't really do cache-aware scheduling on those machines.
Well, if you have an L2, you can feed that mask in.
That's true.
This is one of the things I still need to make happen, is that currently I think we disable it if we find a single LLC. But I think it makes sense to fall back to L2 masks if they're not single CPUs in that case.
So in this case, I mean, this would work on the Ampere machines, but since they promote everything, they don't have cluster anymore. So I don't know how this actually will work on those machines.
So having that many CPUs in a single cache coherent fabric is just painful.
It doesn't fit very well to the existing structure in the Linux kernel right now. That's true.
For a whole number of reasons, it's painful, and it really makes sense to try and subdivide this, especially if it's not a uniform mesh and you can find boundaries inside of it, even if they're not exposed by hardware. For example, you can do a CPU to CPU cache latency measurement and see if you can find patterns in there. I suspect you will, because it's just too big.
Yeah, this is on later slides. So I just want to explain a little bit what this mesh is. Like you see an example here. So this is like a 8x8 matrix. You have these cross points. You essentially have a 2D mesh network of cross points. There's no central bottleneck, right? Coherency is the caches are coherent across all CPUs. You have the key node nodes, which are the request nodes. Those are the CPUs. You can see an example here. You have the home nodes where the directory and coherence manager sits, and also the caches, the HNFs, and you have slave nodes, right, where the memory controllers are. As we discussed already, the CMN is fully coherent, but it's not uniform. So you have mesh distance differences between those key nodes. You have different distance to home nodes, for instance, or you have maybe also different contention on the mesh links.
So, I mean, NUMA is cache coherent as well, and it could be considered a mesh, but it's a mesh with a imposed topology. So again,
I know
it depends something.
I know. Yeah. You're saying that this is like the distance table has to be there somehow, even though it's not really exposed by hardware. Yeah. So this is just describing as an overview where we are right now in the topology of the kernel scheduler. So Vincent also talked about the select idle sibling, for instance, and all this wake up functionality in fair.c. This is all happening in this domain level here. We call it multi-cluster. You have this is showing you the CPU mask, obviously from SMT towards NUMA, this is growing. And on the highest scheduler domain, you have all the CPUs of your system in the CPU mask. And I already said some of the exotic examples, Ampere 1 with these 2 CPUs on the Snoop control unit getting promoted. You have AWS Graviton 4, which is a new verse v2, where we have only one single MC domain with fairly big number of CPUs, 96. There's nothing else. There's no real hierarchy here. And if you compare this to, if you compare this to AMD or Intel machines, this looks quite different. Yeah, and
so I think Intel has some chips with ridiculously large LLCs as well.
yeah.
I've been suggesting that we find means to.
I mean, I have seen a lot of patches from you where you said you even have like a debug thing where you slice and then you prove something.
Many of the smaller Intel systems are just a single LLC, and for me to play with all the multi-LLC stuff, I just did some horrific hacks to artificially split that thing. I did a simple modular, I think.
Mm-hmm.
You go here, you go there, you go.
but completely without any, just slicing.
Whatever. Yeah. And for some workloads, that's enough to actually improve things.
Exactly. This is also what we did. Yeah.
Did you find degradations as you did that?
Yeah. Some of them are actually worse off, but it's. But I think it was Sapphire Rapids, and what comes after that. So the biggest chips that we have are like 64 in the single LLC. But if you run them with subnormal clustering, it'll actually split that up into smaller nodes. So there is hidden topology there. It's just not exposed. And I've been suggesting that we expose this.
This is your discussion about like the new way of checking CPU mask, where you would have to have the CCD and this stuff in your.
Also, yeah, the topology thing keeps coming up.
Yeah.
So with the CPU mask, it is basically to minimize cache line contention by making sure that your cache line is used by CPUs that are in proximity.
Mm-hmm.
Because current CPU numbering and cache topology are strictly speaking completely unrelated. 2 CPU might be next to each other in CPU ID space, but have vastly different cache hierarchies. So it has a renumbering. On x86, we have the APIC ID, and that per necessity is better localized than the CPU ID. When the CPU ID is basically to the width of Bias Monkey, and traditionally order reflects that Windows schedules better.
Okay.
So yeah, random stuff. But yeah, the big LLC problem is definitely a problem, also for ports.
I think this is what it looks on ARM, just for everybody. Like we also have like MPIDR registers, like you see them when a CPU boots up early. So you see the physical ID to logical CPU mapping. CPU1, this is those CPUs, you know, when you go for each CPU, for instance, and check in software, like you want to do stuff on a CPU mask. And then what we have, and probably the x86 guys or AMD guys don't have, like the topology information is not in those registers for us. Like we have affinity levels, but it's not really telling us any topology. We have like another step, that's the processor property topology table in ACPI. And this is where our firmware guys essentially map ACPI processor IDs, which we get from another ACPI table, to processor hierarchy nodes, and they described leaves like CPUs, or like what we then form into scheduler domain CPU masks. So we can also play with these kind of PPTT table to change and rearrange stuff.
Yeah, but you can parse all this on the boot CPU before SMP bring up, right?
Yeah.
Yeah, so then you can go artificially renumber stuff so that it actually makes sense if you have to.
We just have to know what makes sense.
Right.
Okay, no, that's fine, cool.
So for x86, we've had problems for a long while because we discovered much of this during SMP bring up. So we didn't know the machine topology until the machine was online, at which point it's too late to fix. But Thomas fixed a lot of that a few years ago.
This was like the big topology rewrite, like 2 or 3 years ago. Yeah, sorry for switching back and forth in the slides, but it's better to align to the discussion. Here you see some of the recent patches on the list, and you can see that also there are more and more also ARM servers showing up with test results. So this is obviously only like Hackbench or Shetbench, and the difference in the LLC size or the not having any LLC size, it's not really showing, and it's not really being tested, right? It's just like Hackbench numbers, they look okay, so okay, we continue. But I think Ryan from the kernel team also did this kind of next body EVDF alignment. I think we enabled it by default, and then he said he had some problem with the MySQL HammerDB, I guess, and then we took it back. It's good to see that those test results appear on the list.
Yes.
They not necessarily have anything to do with it, with the LLC size directly. So what ways do we have to force like an optimal MC size? First of all, we can just slice, like we already described or discussed, your 128 CPUs into smaller chunks. Then we have the possibility to also manipulate and so rewrite the PPTT tables and feed it back. We could use some kind of cost model for mesh interconnect latency costs between CPUs or CPUs and caches, question mark. And then this is like the management dream, to have like this kind of boot time benchmark, doing this with micro benchmarks, figuring this out on the fly and then rewiring. But this is like
so x86 had something like that many years ago, and we took it out because you had boot variances. You never had the same setup.
It's not good.
I think it was we measured the LLC cache latency and used this for task hot determination and a number of other things. This is around 2618 or thereabouts that it got taken out because it made benchmarking a nightmare. Yeah. Because every time you reset your machine, the value would be slightly different and the numbers would be different and everything different and headache.
Yeah. I mean, this is also something, this has nothing to do with the technology itself, but I think everybody doing this kind of benchmarks on mobile devices or even on servers, you can do your Hackbench, you can do your Shetbench, and you can reason about the data. But when it comes to the big testing afterwards, you rely on different people to do this for you. So, and this is exactly the interface where something like this probably would cause more harm than be beneficial.
Yeah, I mean, it just influences your own run-to-run variance. And
also for,
if that's not consistent, then
true, yeah. So what this is just an example what we did. This is all early work right now for us as well. We use the Ampere. We use different servers like the one I already talked about. We run different benchmarks, Shetbench, and etc. Some of them were already mentioned in different talks during this OSPM, and we just sliced the MC. One thing to notice here is it's still before config shed cluster became default. And on the right-hand side, you see the proc shed stats on an Ampere Ultra. So if MC span is 0, you essentially don't have any MC. And then if you set it to 2, 4, or 40, maybe you see that the mask is changing. In this case, it's viewpoint CPU 0. And what we then did on this machine, here you see the different MC sizes going from 0 to 40. This is an example with shed bench. So you have as metrics, you have the wake-up latency. I think you also use shed bench. Like we talked about this yesterday already. Like we have wake-up latency. We have, so that's the time between wake-up and actually switching the task. You have request latency, which comprises wake-up latency, but it's also like the message goes from the message thread towards one of those worker threads, and the message comes back. And then you have requests per second, which is the total number of requests done in this time. What we have as another parameter here is number of threads. So we go from very underutilized 80 CPUs. We run 160 as a 2 NUMA node machine, so we run only on 1 NUMA machine, node. The other one we use for the system. So we try to isolate the test itself, and we change the number of worker threads from underutilized 53 to heavily overused utilized 246. And this is an example where you are somehow in the position where there is contention on the run queues actually shows in your test results between latency, wake-up latency, request latency, but also request per second. And noticeable here is like if you have 0 CPUs, so there's no MC domain, obviously the wake-up latency is very small because you don't look for an idle CPU. Request latency is higher, so that's probably telling you you don't do the best scheduling decision, but also RPS is high. So it depends on how you see it, what's more important for you. Because it's not a one-to-one correspondence between RPS and latency. There is also contention on the run queues, and you could see that 106 threads is essentially the problem where it actually changes from being underutilized and to a massively overutilized situation. And maybe on the other slide, this is better to see. So the only thing we could see here is with 80 tasks on an 80 CPU system, you see that if you increase the MC size, yellow is 40 CPUs and pretty dark is 0. You see that with constant wake-up latency, you see a little bit that the RPS goes up. And so also the request latency stays constant, and you get a little bit of more requests per second. If you switch to this contention limited need issue with 106 tasks, you see kind of the opposite. You reduce, you treat up essentially RPS against request latency. And there are cases when you are completely underutilized, there's nothing to be gained. And also if you are heavily overutilized, it doesn't make really sense. But this is a normal scheduling problem. So you have to be in the zone of 80 or 106 tasks on this specific setup to reason about what you essentially change when you go from 0 to 40 in MC size. We were hoping to see better results here, but one thing I have to say, and we talked about this already in the talk from Vincent, there are a lot of, if you do a wake up and fair, there are a lot of exit criteria before you essentially go into the MC domain and look for an idle CPU. After wakefin, you have 2 CPU choices. You have the target CPU, you have this CPU where the scheduler runs, and you have the pref CPU of the task where it was running on before. And if one of those is already idle, we don't actually go and search for an idle CPU. And there are more exotic exit or early exit criteria related to recently used CPU, and some K-worker thread is there's special treatment, so sometimes you hit them as well. Not in this case, but it's not really a one-to-one correspondence. So if we want to if we would have like to beautify those test results, we would probably disable all those exit criteria, and then we would see something more. So we would probably see better results here. In terms of that MC size, makes sense to tweak it on those machines as well. So far it's all just we sliced completely arbitrary, but the what will happen if we minimize the distance of the MC domains? Like this is just like here a picture which shows the gray things are the home nodes, so that's cache location. It's not a real CPU, right? It's just like a little image here. And the color code shows CPU nodes, request nodes. And if lighter color means they are closer to the cache location. So you can have, you could essentially create like a mapping of cache or CPU cache distance, or even CPU to CPU distance. I think we mentioned this already, or I mentioned this already. Yeah, we can have this kind of we can create this heat map running like running small benchmarks to figure out what the cost is between those entities. I think also people have done this already. There are papers out there for ARM servers who show this kind of thing. But the issue is then, how do you use this information to create multi-cluster domains? Because there is no hierarchy in this information. It's like you have some good CPUs, you have bad CPUs, but how do you cluster them then do you cluster them, put some good and some bad together, or I don't really have a good idea there.
In this particular picture, you can draw a line. Just,
yeah, because they are not really, I mean, the home nodes, there is no hierarchy, right? It's all like for all. And some of them are bad, some of them are good, but it doesn't really fit into the structure of the scheduler domains.
So what do you actually measure here? It's CPU to CPU latency? Or?
No, this is just, we haven't measured anything. It's just something we try to figure out, is it possible?
Those things are to the CPU.
The home nodes.
What does it look like if you measure latency to memory? Because there are multiple memory controllers on that system, right?
That's true. So not to the home nodes, you mean to memory?
Yeah.
No, we haven't done this work, right? I'm just asking, like, if we would do this work, then could we use this information to create like reasonable MCs?
I mean, you could do like you measure CPU to CPU distance. You do message passing, and then you cluster them together by distance, kind of like a NUMA table.
You mean it's just CPU to CPU, and then
see how long it takes to go through the memory system for whatever is leaking them.
I mean, I know that there are different of those micro benchmarks, and they all function differently.
With LM bench, you can get that.
LM bench is used, yes.
On SunderX X1, and there was weird topology that didn't.
Did you put it in Confluence back then?
Something.
Okay, yeah. So maybe this will work, right? Like you could find clusters doing this like this.
Yeah, and then there's the CPU to CPU, but also CPU to memory might also give some clues.
Mm-hmm.
Yeah, it's a bit of a mess. Oh, mesh.
Yeah.
CPU to memory, you essentially would have something like asym CPU capacity, because if you have a cluster of CPUs that are slower, let's say to memory, and others that are faster.
You get NUMA-like.
I mean, at this point, show them in NUMA,
yeah. It's I mean, I would map this into NUMA more than LLC.
Yeah. Yeah, I mean, this is probably what we're going to be trying right now as research, right? Like, and I mentioned this already, like the next step is to convincing the guys doing the test beyond chat bench and perf bench.
If you talk to the hardware guys and express the problem, are they aware that there is a problem?
I haven't personally spoken to them, but I know that like Arm is a big company, right? Like different parts of the company might have done this. So for me, it's now a task to figure out who essentially has more information on this than me. And our task is as a performance team to combine like how the scheduler look like with this kind of information, because very often you see this, there's a lot of intelligent work going on in silos. And this is one example where we want to bridge. If there's something to gain, I mean, we don't know. There might be something to gain on the level of pure engineering, so we get all excited. But if you hand it over to the test teams later, then they say, okay, what is the fuss about? We don't see anything, or it's getting worse. For instance, like this also like a possible outcome out of this. But I think it seems to be interesting, and we don't want to be seen as somebody who we didn't say anything when it was still something fresh or interesting for others. Yeah, so I think all of the discussion points I already handled during the talk. So this is kind of just a summary of what we discussed. And with this, I think, are there any more questions?
So yeah, the search space, 16 to 24 might be nice, but there's definitely workloads that like spending more time looking for an idle CPU in order to get the idle CPU than other workloads. As with everything, it's a pain in the ass. But in general, I think 16 to 24 CPUs in a cache domain is.
Yeah, this is what I thought, but it's very hard to find evidence. Nobody tells you that.
So on the Sapphire Rapids, and Granite Rapids is, I think, after that the big ones. It's becoming painful. You really see that the LLC searches are taking too much time. I mean, AMD had the opposite problem. I think with Zen 2, there were chips that had 3 CPUs in an LLC.
Oh, okay.
The next CPUs was 4, and then 1 got cut, and then you had these dinky little L3s. But the latest chips are better.
Okay, so you guys learned your lesson. How do you deal? Like, do you talk to the hardware guys, or it's just pure coincidence that they get better? Okay. This is what I thought. Okay. Yeah.
For skip bench, did you really try to look at any traces while looking at the data? Because I haven't really tried like running it alone recently, but I've been trying to stress the system, and I found that sometimes you can end up with a worker thread on the same CPU. This can really skew your P99 and max values a little bit, like these random occurrences. So that, I mean, if you really want to look at this, you really want to verify or at least hack skip bench to enforce each worker threads end up in a single CPU. Otherwise, your test results can get a bit.
Yeah, it's what Vincent also said. It's all racy. So
yeah, because I mean, I'm not sure if you saw my email with Skid QS trying to really prove it with Mick, and I was seeing lots of this, like, hey, 2 worker threads on the same CPU, not a great. And when it's running alone, I'm not sure you can guarantee you never hit this, but this can easily skew your max and P99 values, because even if it happens for a very short period of time, your P99 and max values will start looking worse. So potentially not really measuring the impact of search space, but the impact of bad scheduling decisions under very specific circumstances that are really hard to see and search very easily.
Yeah, that's what I was showing in my graph yesterday, which you had a bunch of latencies clusters in the small interval.
Yeah,
so you have a long tail of outliers.
Yeah, okay.
So it might, if you only focus on the 99th percentile, you will be missing out the other part, in which is the normal behavior of the distribution of latency.
I don't really have great experience with all the server market stuff, but like from mobile world, really like, I mean, the speed of the decision is really less important than the quality of the decision, especially with power management and all this kind of stuff that can make like a bad decision really much more impactful. Which I don't know, to be honest, how to quantify. That's the hard bit of it, of like, sometimes it is worth to spend more time to find a better decision, because sometimes can be very high.
Yeah.
The cost can be very high. Like if you don't go to idle CPU, you could coexist with a task that is busy, and then you see higher latency more than actually spending more time searching. And how do you find out? And I don't know, but I think it's nice to think about, rather than, because I see a lot of people posting results, just try to see like how fast can I make this decision, but like what's the quality of this decision under different scenarios. I mean, quality is quite hard, but I think in practice, what I see, the quality matters more than the speed.
But maybe more on mobile devices
are impacted by these quality decisions.
Quality is more like from mobile devices, battery.
No, it's just basically latency as well, because like, I mean, if you end up with a code running at a lower frequency for it to ramp up again, or like you end up with a task that is busy, you have to time slice, because at least on mobile we have AS, so you end up packing more. But like even in real world, you can end up packing because system is really random, right? In real world, you just have all random tasks running all the time. So just like accidentally being somewhere collocated with something that's not great.
You're right. Checkbench, you could examine like traces and maybe see a pattern and change it. But then the next step into the real, I mean, I tried to analyze DC Perf, MediaWiki or MySQL, and it's really hard to.
It is hard to look at real workloads because you don't understand them.
Postgres workloads are nice.
Yeah.
Maybe memory controller is a good idea. Power trend, something like that is done for MCC. And hardware tells you which cluster you belong to based on how close you are to your memory control. Only hardware control.
Thanks.
For the different plates and like how far to different cache and how far to the maybe the mass, so maybe it will have different power cost. It will have different power model for CPU.
That's true, but we are dealing with servers here. We don't really care about power here. It's not about mobiles.
I mean, the power model may indicate more accurate number on how the CPU delivers same workloads.
Servers don't have the power model. Servers don't use the power model.
Yeah, so we have to make a distinction. Those are actually really different worlds. Since we have done mobile before, it's also hard for us. We always fall back into that kind of thinking, but on the server market, nobody's really interested in those things.
When you wanted to build the the CPU topology for different for different schedule domains, maybe it can be referenced like a similar power cost can be the CPU in more similar schedule domain for.
I think this is like mobile stuff. This is super important and also hard to do. And but here we are just interested in latency and throughput.
So for at least an actual split LLC architecture, it's much more costly to have a wrong task placement, right? Because you have to pick the data from the other side. You don't have that problem, and all that you get, you might care about is to even out the utilization rate. So in that case, would it make sense to have like the entire package as a search space for wakeups, but you divide the LLC further for load balancing so that you can look at pockets and try to balance between them?
That's also not consider the same kind of hierarchy on both sides.
Okay, so let's assume we're going to do something to remap the scheduler hierarchy based on TTL, which is a topology description. and we know what we want to do. Let's forget that we don't know what we want to do. So let's assume we did know what we want to do.
Fair enough.
Right? Where do we put that? Know where we would plug in a module, or is it art specific? Is it something more generic? Is it
So this is all architecture code.
yeah? So it's canon again.
Perfect. Or we get Rutland to sneak in.
It's very busy. Just
Fair enough.
Yeah, we have plenty of time. We have like 20 minutes.
Okay. You look hungry.
Right.
Okay, so thank you all for all those good ideas and for listening to me.